Hello, I'm Haiguo from Georgia Tech. I'll present our work, a metric for quantifying UWB ranging error due to clock drifts. Ranging is one of the most common and effective method of localization in UWB systems. Over the years, many ranging protocols have been proposed for different purposes. They may have very different communication protocols, or they may use the same communication protocol but different formulations. The methodology, they can also be divided into time of arrival and time difference of arrival approaches. Now consider if we need to build a robot navigation system or a museum tour guiding app using UWB localization. Which ranging protocol should we choose? And how do we quantitatively compare one protocol with another? In this work, we try to answer these questions by coming up with a metric that can map each protocol into a data point. And simply by looking at where the protocol data point is, we can get a sense of how good the protocol is and how it compares to others. But first of all, what makes one protocol more desirable than another? To answer that, let's use two-way ranging as an example. In the single-sided two-way ranging, only two messages are needed. We can simply subtract dB from RA, then divide by 2 to obtain the time of flight. In an ideal world, that would work, but in reality, the clocks in UWB devices are not perfect, and the clock frequency drifts. Therefore, the measured time intervals are always slightly different from the actual time intervals. We can analyze the error from this tiny clock drift by subtracting these two quantities, and we can apply dimensional analysis on this final form. Since rho, the time of flight, is on the scale of nanoseconds and multiplied by a small number, this first term is negligible, but dB is usually on the scale of milliseconds, and it depends on the number of instructions executed and the radio turnaround time for specific platforms. dB multiplied by delta, the second term is on the scale of nanosecond, which is, when we convert it to distance, several meters. Therefore, single-sided two-way ranging is not really a desirable ranging system. Next, let's look at double-sided two-way ranging. So double-sided two-way ranging uses one more message. For this time of flight formulation, we can again derive the clock drift error and apply dimensional analysis. Although the equation still contains dA/dB that are on the millisecond scale, it could approach zero if we make dB equals dA. Therefore, for double-sided two-way ranging, under certain system parameters, clock drift error can be eliminated. Well, the alternative double-sided two-way ranging takes it one step further. The communication protocol is the same, but the new formula eliminates the clock drift error completely. So let's compare these three ranging systems head to head. Well, the first observation we can make is that the double-sided two-way ranging and alternative double-sided two-way ranging are better than the single-sided two-way ranging because they can achieve better minimum clock drift error. And the second observation is alternative double-sided two-way ranging is better than double-sided two-way ranging because it's more robust under any system parameters. So we have seen the minimum clock drift error and the robustness can set apart different protocols. So the question is, how do we quantify the minimum clock drift error and robustness? In this work, we do it through numerical simulations. We've plotted the clock drift error versus different DA/dB values at small increments. We notice that the minimum ranging error is manifested in the minimum value of the error, and the robustness or the dependency on system parameters can be represented by the gradient of the error. Then we can define these two quantities to be the two dimensions of our metric, which we call the EG metric. Using similar method, we plot the error over response delay for 4 more ranging protocols. In this paper, we evaluate a total of 7 protocols for both TOF and TDOA systems. To compare the 7 protocols, we plot their EG metric together. The protocols in the bottom left corner are the most desirable ones because they can achieve low error without any dependency on the system parameters. The protocols can now be compared pairwise by looking at the relative position between them on the EG plot. We package this tool into MATLAB functions that are open sourced. The user can simply change the protocol expression and the timing relations. They will be parsed automatically, and the results can be compared with other works immediately. We envision this EG metric can be used by researchers to analyze and compare protocols when inventing new methods. Also, localization application developers can use the metric to choose the right ranging protocol and parameters. If fusion is needed, people can use the metric to estimate the amount of uncertainty in the ranging measurements for the chosen protocol. Thank you all for listening. For more details, please refer to our paper.